All right, welcome back to the Kitchen Research Group. Today I'm going to expand on some work I previously talked about on generative approaches to inverse problems and expand that idea to generative approaches to optimization. So the idea here is that we want to find a way to solve some optimization problems that don't involve nonlinear programmer solvers that iteratively get their way to the solution. So this is work I did with Victor Alves, and you can see us down here looking at some ways to avoid needing all these gradients and iterative processes, and I'll talk about how we came about to view this idea. So the main idea is to think about the DALL-E and other image generators and how they work, and get some inspiration on how we might apply that in science and engineering. So these big image generators are trained on large collections of images, and the goal is to learn the statistical distribution of that image space. And then once you have a distribution, we have ways to sample it, and by sample it, I mean generate new images. So the particularly interesting thing about it is not that we can simply sample and generate images, but we can condition the images. That means we say, make an image with a flower, and then we get an image with a flower. So I started thinking, if we could do that, what if I could say generate a sample that was a solution, and I could condition it on the solution, then I would just directly generate samples that are solutions to problems. Now, how do we connect these ideas? These images are just arrays of pixel values, and you can flatten the array into a one-dimensional vector. And that vector just has numbers, and then what we do is learn the distribution of those vectors, and then we can sample new vectors, and if they're images, we get an image. But if we represented, say, an engineering problem as an input and output that are concatenated together, then we could learn samples of those vectors. And then if I could condition to say, give me an output that I want, and it generates the input, then we've basically found a way to do generative modeling for optimization. So that's what I'm going to talk about today. I did talk about this in the last video or two on new ways to solve inverse problems this way, where we have, say, some inputs here, a red, green, and blue level for an LED, and we detect all of the wavelengths that come out. And if we build a generative model, then I could say what output I wanted and generate the inputs. And you can find that article on ChemArchive at this link here. And it allowed me to solve this inverse problem in a new way that used the generative model. So we'll expand that today. So here's what I think of in the generative model space. This is a simplification in some ways, but it's going to work for the particular model we use today. So we either think of it as a model of the joint probability distribution. That means how are all of the variables, inputs and outputs correlated. And if we know all the covariance between them, we can generate samples and then conditionally sample it in a way we want. There's another way, diffusion models and normalizing flow models, that learn to transform one distribution into another. I'm not going to talk about those today, but they also work in this process. And then once you train these models, you have to train them from data. So these are data-driven approaches, and technically we might call them a surrogate model for the data because we don't have a first principles way to compute them. So why is this interesting? Mostly for me because it's new and different. I didn't know how to do it before, and now we do. So there's a way that we will use them that once we do the training, we avoid nonlinear program solvers. That means no initial guesses and no iteration. I'll show you what we do is simply say what we want and then generate samples of it. And I'll show you a bunch of applications here on root finding, minimization, parameter estimation, and state mapping. And because we can draw samples from this distribution, we can also generate distributions of solutions, and that allows us to do some measure of uncertainty quantification. So at this time, I'm not going to try to convince you that this approach is better than anything else. The nonlinear programmers, program solvers, some of them are very sophisticated, very efficient, at what they do, and we don't do it more efficiently, we just do it without them. So it remains to be seen if there is some, magical scenario where this is superior to things. But I'll show you a few ways that it's better, and then you'll see plenty of ways where it's different. All right, so I'm going to focus on Gaussian mixture models exclusively for this set of examples. And these are, this is an example where we have some noisy data, and we kind of fit different regions with different Gaussians, and then the Gaussian gives us a probability distribution, and then we can calculate what's the probability of getting, if I say x equals 1, then we have this probability over here for getting y. If I say x equals 3, we have this probability. And if I say y equals 0.5, there's a probability here and a probability here that we can draw samples from. So it's a very simple model. I think it's a little bit like a piecewise linear model, but with Gaussians instead of piecewise linear. It's a little bit like a ReLU neural network in the sense that those are also like piecewise linear models. It's like a linear decision tree where you have, say, this region, and this region, and in that region you use this Gaussian for inference, and it's a little like a k-nearest neighbor model as well, except that instead of just picking the average or something like that, you could fit a Gaussian to it. So it's a pretty straightforward model. They're pretty easy to fix. We use the GMR package that builds on sklearn, and you just give it data and fit it. The conditioning is sort of a new idea for me, so I'll just take a second and kind of go through it. Here we have one Gaussian, and you can see we, an approximately normal distribution on y, also on x, and it's quite wide. But if I say, give me a value of y equals 1, then we can update the conditional probability of x, so it's only in this red window here. And so I show that over here. Here's the full x of all the data, and the orange one is the conditioned x, so it's a much more narrow distribution that's centered around 1 in this case. So this is just an alternative way to think about how do I model this data. You could fit y equals x and find the slope is 1, or we can use this Gaussian, two-dimensional Gaussian with covariance and sort of achieve the same goal, and then we know this is the distribution of x that comes from it. Okay, so let's just get to some examples. Here, if I want to find the roots of this function here, the roots are where it intersects with 0. What I can do is generate a lot of samples of x and the corresponding y. Those are the blue dots. We fit a GMM. This is in the paper. This is the function that does it. It just finds the best GMM for it. If you look really careful, you can see, the red line fits really well. It's a little funny down here at the bottom where it looks like it's just fit one Gaussian across the whole range. So it's not super accurate right here, but it's also not terrible. And once we have this GMM, this is sort of the syntax to condition it. I'm going to condition on the index of 1, that means index on y, and then I give it a value of 0. So basically I'm generating samples of x where y equals 0, and we get a histogram that comes out. So here I generated 1,000 samples, and about 300 of them correspond to this root, and 699 of this root. And there's one spurious root over here, 1 out of 1,000. I don't know how to explain it. It might be just an artifact of this being a surrogate. So you have to be a little bit careful in making sure the surrogate is sufficiently accurate and you have enough data and enough Gaussians in here. This solution, this is a fourth order polynomial, so technically there should be 4 roots, but we only find 2 of them, the 2 real roots, right? Over here you can see there's evidence that there should be 2 imaginary roots, and we don't find them here because we only sampled on real values of x. It is possible we can sample on x real, x imaginary, and y real, y imaginary, and then we can get all of the imaginary roots and real roots out of this process. So it's quite flexible in what data set you build for managing that. We can do any other value of y as well. If you wanted y equals 2, you would get these 4 numbers that come out, and that might be interesting in some case. Okay, unconstrained optimization is also quite simple. There, what we do is build a model that looks at the inputs x and the derivatives y prime. So you have to be able to calculate derivatives. And if I build a data set and build the GMM, then condition on y prime equals 0, what you see here is we get the 3 stationary points, this minimum, this maximum, and this minimum, and we get them all at once. You generate looks like maybe 100 samples or something, and you get all 3 roots at once. I think this is a benefit over a nonlinear program solver like minimize or root, because there you have to make an initial guess, they're local, and they get trapped. Here we get all 3 of them kind of at once after we've built the model. Now it is a little bit subtle because we have minimas and maximas where y prime equals 0, and in the paper we show a variation where we can add a final column to our data that is an integer, and the integer could be, say, +1 for a minimum, -1 for a maximum, based on the sign of the Hessian. And then we can sample for y prime equals 0 and the Hessian sign is positive or the Hessian sign is negative, and that allows us to make a generative solution for where we have a minimum or a maximum. Now, it's necessary to do that because when we condition, you have to condition on a number, not a property like greater than 0 or less than 0. So here we were able to put a binary discrete variable for whether the Hessian is concave up or concave down, and then sample it, which I think is pretty interesting. This is the unconstrained optimization case. We can pretty easily make an equality constraint. We just have to modify our objective function so that we are solving this Lagrange function. So this is a pretty standard way of incorporating an equality constraint. We build a Lagrange function, and then we build a model on the inputs and the derivatives of that Lagrange function. And at the solution, we know these 4 derivatives are 0. And so down here, we construct our Lagrange function by adding this term here for the equality constraint. And then we generate data. I use JAX to get the Jacobian. And over here, I'm conditioning on DL, all the DLs being 0, and we give them the values here. And then we just make predictions and find what the solution is, and it works really well. You can see the paper for like all the details and the actual solution. It works even though this model, this isn't a great fit in my opinion. Like these magenta points look like very well fit, but there's a little bit of noise in these other derivatives, but we still are able to get a very high quality solution. I think with more data and more Gaussians, you might get a better model, but this worked, and I thought it was kind of sufficient to demonstrate the proof of concept. All right, with inequality constraints, we have to do something a little bit different. Here we use a barrier function, and this is another kind of standard modification that you put this barrier function in here, and the derivatives of this function now are 0 at the solution. And so here we just create our barrier objective function. Mu is a little number that ideally you want to run this to 0 and see where it converges. We generate our data here, and then I just make a prediction of the dB, the barrier function derivatives being 0, and we get a solution without having to go through the nonlinear program. So I find that also pretty helpful to solve inequality constraints. We can do parameter estimation if we think about it in the following way. So with a parameter estimation, we'll typically have a model. So here I have this plug flow reactor example where we have changes in the molar flow of A and B that depend on these rate laws, and the K1 and K2 are unknown. Now, if I generate data which I can generate over a range of K1 and K2, then I can get a corresponding a set of output observations. So if I look at a range of K1s and K2s and run a lot of simulations and have then a corresponding set of outputs, then all I have to do is say, well, what output did I actually observe? And solve that inverse problem to generate the Ks. So that's what I did here. So suppose I observed these particular outputs, that leads to this distribution of the Ks, that K1 and K2, and you can see that we get a distribution here that gives us some uncertainty about what the true value of K is. Now I will say the uncertainty here is due to the noise, is due to the lack of fit in the GMM. The data that I put in here has no noise in it. It's you put in a K1 and a K2 and some initial condition and you integrate it forward. So there's practically no noise in the actual data. But over here you can see there is a little bit of a small error associated with the GMM and what it's actually able to predict. And so that's what this uncertainty represents. If you used a more comprehensive GMM or had more data or a better model, then this line would lie on a parity line and there would be much less uncertainty up here. But if there was noise in the data, it would be captured in here as well. So I think this is a super interesting way to think about generating parameter estimations from observations that I've never seen before. Of course, it doesn't mean it hasn't been done. It just means I haven't seen it. Okay, and then I think this is the last example of state space mapping. This is work we've done a lot of in inverse mapping and other publications that I did with Victor earlier. And the idea is if I have this input-output map, I want to find this region over here in red, and I want to know what is the corresponding input space that would give me this red circle. And here we have this generative model for input-output, and given all of these points, we simply generate this red region over here on the input. It's not quite as smooth as the analytical surface down here, but the analytical approach down here requires you to know the model, and this is a totally data-driven way of doing it. There are other data-driven approaches, so we could have learned a neural network forward and nonlinear program back, or you could also learn the backward model. So this is just another way of doing it that allows us to map in this joint probability context how to do it. So I think that's also pretty nice. This approach down here relied on automatic differentiation and path integration. This approach up here relies on a probability distribution and sampling. So they're complementary in that sense. All right, so there are a couple of caveats in here. I think the GMM is data-driven. It doesn't extrapolate correctly outside the known data. So if you start generating samples outside the data you've trained it on, bad things are sure to happen, or incorrect things are sure to happen. The Gaussians basically extrapolate linearly outside the data set, and that's not what your model is probably doing. The other thing that is true is that regions that have a very low probability, they're hard to sample. So if your solution is like a needle or in a very small space, you might miss it by sampling. And that's a feature, I think, and an open research area for improving. And then you may need a lot of data for nonlinear systems. I showed you that the GMM is kind of like a little piecewise linear model. And so if you have a high degree of nonlinearity, you need a lot of little pieces. That's not a problem like in itself, other than you need a lot of data to capture the nonlinearity and then a lot of GMMs. There may be other models like the normalized flow or diffusion models that are also generative that may be better at fitting that kind of data or in some way. But these are kind of one-way models. That is, you say when you train it whether you're inferring forward or backwards, and the GMM is either way at inference time. So I kind of like that. I think those are the main caveats. I probably talk about a few more details in the paper that you can check out.
So I'll wrap it up here. It looks like, so generative models are surrogate models trained on data. I don't know any case where you can take a model and generate the generative model. There might be one, but there probably aren't many. So most of them are going to be trained by data. I think of them as sort of air quote complete models that really encompass the concept of forward and backward models. And then you decide at inference time which way it goes through conditioning. And then once you do that, you find solutions by sampling. So you say, I want solutions where the derivative is 0, or the function has this value, or some other kind of condition that you can think of that's a number. And then you sample it, and you can either sample the mean, so you just get the most likely number, or you can generate distributions like I showed you. And then you can do some kind of uncertainty quantification for that. So you have lots of applications in optimization. I showed you root finding, parameter estimation, minimization, maximization, state mapping, probably more. These are the main ones that we came up with to demonstrate it. I focused on the GMM because it's so simple. I like it. It's easy, but future work will get into normalized flows and other kinds of approaches. And I think there's a lot of room to build understanding in where these things are good, how to do things like feature engineering, data scaling, iterative refinement, etc. I think there's a lot of room for learning about generative models through this optimization space. So that's it for this. Thanks for coming, and hope you enjoy.